Go on, and before I introduce the next speaker, I should introduce myself. I'm Martin Abraham. I'm a counselor for the INEC division, one of the co-editors for the book, and I'm delighted to be here today to be able to join you and enjoy this great session that Bill and Mike already kicked off for us this morning. I want to introduce our next speaker. Our next speaker is Glenn Lipscomb. He comes from the University of Toledo, where I knew Glenn for 10 years, a good friend of mine, and he's going to tell you all about...
Huh? You left us.
Yeah, and Glenn, in addition to being a professor of chemical and environmental engineering, is a past president of the North American Membrane Society and still the editor of the NAMS Journal. So he's going to tell us all about membrane separations.
Well, thank you, Martin. And Bill and Mike, I want to thank all of you for the opportunity to participate in this very special issue of the ACS Symposium series. It's been a real pleasure. And I apologize for the delays in manuscript. Well, I'm going to briefly go over drivers for this industry. Sven has actually talked a little bit about some of the things I'm going to talk about. Then I'm going to mention some of the enablers that have allowed membrane technology to play the role it has. Then talk about its past, present, and future. Each of those areas very briefly. Well, the primary driver for, at least I think the primary driver for interest in membrane technology is the growth in the world's population. If you look on this chart here, you can see that by the year 2010, we're anticipating about 7 billion people on the surface of this Earth. Now, along with that's going to become a certain amount of demand for energy, and that's shown by this green line here. It's anticipated, well, right about now, we're using 10 billion tons of oil equivalent per year. And if you extrapolate that line on out to the year 2010, you can see that we're going to have tremendous growth in our energy consumption as well. So, what this says is that we can anticipate that population and energy use are going to grow. The energy use is going to grow because we have more people, but also because the world's population is becoming more affluent. As they become more affluent, they tend to use more energy. There's a trend or a correlation between growth in the gross domestic product as well as energy consumption. And I think that's an interesting question. Can we decouple the growth of those two things? Can we have the GDP grow without energy growth? And it is possible. Well, if we just extrapolate the data that we have, we can see there's about 3% energy growth per year, which over a couple decades means we're going to increase energy consumption by 70%. I think that's not sustainable. I think all of us would agree that's not sustainable given our current energy crisis. But there is hope. At least in the US, there's been a study done by ORNL, which they've identified 200 trillion BTUs per year of energy savings that are possible by just looking at separation processes that are used industrially and trying to modify those separation processes in an appropriate way to reduce energy consumption. Now, how can we do this? Well, we might start thinking about the end of the thermal age. Most separations are done using thermal or equilibrium processes, industrial, such as distillation right here. However, if we can switch to separation processes that make use of chemical potential differences, if we can maintain two streams inside a device at different chemical potentials, then this can be a lot more energy efficient than an equilibrium separation process, this rate-based process. Now, for this rate-based process to work, at least for a membrane process to work, we have to have a material that allows selective transport through it. We have this gradient in chemical potential across a material, say a membrane here. It's going to drive transport of the red and the green species across it, but all we want to allow is one of them to go across, say the green. So somehow we've got to come up with a material that will allow that selective transport. And there are several ways of doing that. One, for instance, we can make a porous material like this blue block right here that will allow different shaped objects to go through. For instance, it will prevent this big blue circle from going through, but it will allow this red cylinder to go through if the line's in a proper configuration. So we can have size selective separations. We can also have separations based upon charge. If we are charged the surface of this membrane in a positive way, then positively charged molecules will tend to be repelled by it, and negatively charged molecules will be able to pass through it more freely. We can also make use of differences in solubility. For instance, this little green circle right here, if it dissolves to a great extent inside this material and then diffuses through it, we can selectively remove it from something else that doesn't dissolve into that material or has a slower diffusion rate. So the key to membrane processes is identifying this material right here and making use of these different separation mechanisms. Now, there's been tremendous success. So there's one story I think we need to tell as membranologists, everybody, to highlight the importance, I think, of this technology in the future. And I think that we're going to see this played over and over again in different areas. And that's in desalination. What's shown on here is cumulative desalination capacity in millions of gallons per day as a function of time. And there's two lines on here. One corresponds to the capacity due to thermal processes, which I'll mention in a moment, and the capacity due to membrane processes. two interesting things to note about this is that membrane processes don't exist until about 1970. It's all thermal until then. The second thing is that now membrane processes exceed in capacity thermal processes. And in fact, virtually every new desalination project is membrane-based. There aren't any new thermal projects. What's shown over here is one of the largest desalination or membrane modules that you can buy. This comes from Coke. You can see the size of those things. Well, why have membrane processes displaced thermal? That's shown here. This is a plot of the energy required in kilowatt hours per cubic meter to produce a cubic meter of fresh water as a function of the cost of that cubic meter of fresh water for the different processes. So these 2 points, or these 4 points up here in the corner, are the values associated with thermal processes. The MED is multi-effect distillation, and the MSF is multi-stage flash. The two different symbols, the blue and the red, correspond whether we take into account the efficiency of converting a hydrocarbon into electricity. The red take the efficiency into account. In fact, you're only 33% efficient in converting a hydrocarbon into electricity. Well, here's the values for the thermal processes. What we really want to be is down here in this corner. We'd like to produce fresh water and have it use no energy and cost nothing. So we want to move from here down to here, and membrane processes allow us to do that. Here's RO processes, I would say an industry standard a few years ago, an RO process in which we make use of energy recovery. You can see we have a tremendous drop in the energy consumption, a factor of 10 drop in the energy consumption. That's huge. Secondly, we've reduced the cost by a factor of 2 almost, especially if we take into account some of these new high-performance materials. Membranes have reduced the energy consumption by almost an order of magnitude and the cost by a factor of 2. I like that. And I think everybody should hear that, because this says that this is a technology we should be considering in a lot of other areas. Well, what has enabled that? Well, first of all, we have to have material. I mentioned that we have to have a good material. And there have been advances in making materials that have high salt rejection, more importantly, high flux and longevity. These materials have to last a certain period of time. They're going to have to last 10 years, maybe more than that, 15 years. There's also been changes in manufacturing. There's been some economies of scale in the manufacturing of these units. And I think equally important, quality control. In fact, now we can make materials that are uniformly the same quality, have uniformly the same permeability, the same selectivity. And finally, there's been important advances in process design, energy recovery devices. The fact that we need to pre-treat seawater before we run it through a desalination unit. If we don't pre-treat it, then that unit will only last, it will have a too short a lifetime for it to be economically viable. And finally, module design, the fact that we are able to make large-scale devices that work efficiently. What's shown here is a picture illustrating this energy recovery turbine here. We take seawater, you pump it through an RO unit, and what's missing here is all the pre-treatment equipment that goes there. So that's missing, but it should go right here. But after it goes through this, fresh water will permeate across the membrane. That's collected as our product. What's rejected is under pressure. It's a high-pressure concentrated salt brine. Well, we can make use of that. We can recover that energy by running it through this recovery turbine here. And all modern plants have that turbine to help or assist this pump in bringing the fresh seawater up to the appropriate pressure, 300, 400 psi or higher. Okay, that motivates why we're interested in membranes. Try to provide some motivation for that, and what the key enablers are: materials, manufacturing, and then process design. Now I must go into what was in the article that was written for the special issue of the symposium, ACS Symposium series. Talk a little bit about the history of membranes. I think most people would say you could trace back the history of membranes to Nolet's observation that if you have an animal membrane, it selectively allows water across it, but not alcohol. Now, Van Hoff figured out how to quantify that mathematically, and Fick and Graham followed that up with studies of diffusion that allow us to characterize diffusion as well through these materials. But those were scientific discoveries, ones that weren't made use of commercially until much later. And I would argue that the commercialization of membrane technology, you could say, started with the Saline Water Conversion Program Act in the US back in '52. Now, initially they weren't interested in membranes. They just wanted to produce drinking water for the people in this country. Well, they made some progress, and eventually that morphed into this Office of Saline Water. And there, with the Office of Saline Water, there was increasing interest in membranes. And ultimately, a few years later, it led to this key invention, this key discovery of the asymmetric membrane by Loeb and Suryajan. And by the way, they were nominated, or I think they might have been nominated for a Nobel Prize on this. And I think this is one of the key discoveries that have enabled membrane technology. Here's Said Loeb, this is from a web page on UCLA's website showing him and one of the engineers that was making some of the early RO membranes at Cellaver. Well, what they found is that instead of just taking a piece of plastic, which is what they're using for desalination, and pushing water through it, is that they took that piece of plastic, let's say cellulose acetate is what they were using at the time, and mixed that with a solvent, acetone, to make a solution denoted by this 0.1 right here. And they selectively removed that solvent and replaced it with water, such that when they cast a film, at the top of the film, the composition ended up at 0.2, and at the bottom of the film, the composition ended up at 0.3. Now we can envision this being a film or a hollow fiber, as you see right there. Those are the two main forms that membranes come in. But now imagine we cast a film, we're going to selectively remove the solvent, acetone, replace it with water, and we're going to do it in such a way that at the top of the film, we end up with this composition of cellulose acetate and water, and at the bottom of the film we end up with this composition. Now those two compositions differ in a very important way. One lies outside the phase envelope here, outside the binodal, such that we have a one-phase solution here at 0.2. 0.3 is inside it, so we have a two-phase. Now let's remove the water. If we remove the water from the one-phase mixture to this 0.2 here, if we remove it slowly enough, we end up producing a dense polymer film, such as you see at the very top of this slide, this image right here, this SEM. If we remove the water from this mixture right here, which is phase separated with droplets, imagine, of water inside a solvent or a polymer-rich region, if we remove those droplets of water from there, we end up with this porous structure underneath, corresponding to 0.3. What we've done then is create a film or a fiber wall that has a certain thickness, a macroscopic thickness, but the effective dense thickness, where the discrimination occurs between salt and water, can be much, much thinner. It can be confined to a region that's a sub-micron thick, whereas the support structure underneath can be order of several microns thick. And if you design it correctly, if you get this pore structure correct in there, it poses no resistance, very low resistance to permeation, and no selectivity. This is the key innovation right here. Now they make use of this innovation, they started to, making hollow fibers primarily for desalination and also films. What they would do is they take the polymer and solvent, mix it in an extruder, you can mix it before you put it to the extruder, and then run it through a die to form a group of hollow filaments, a fiber tow, just like you would in a textile line, where you make solid textile fibers. This tow then would pass through a couple baths. The first bath might be to set the structure, to cause the solvent exchange that would lead to this asymmetric structure of a thin dense film on top of a very porous support, and then to set that structure and to dry it in subsequent baths, and finally to take the fiber up on a spool, just like you would take thread up on a spool for sewing. So this is how the fibers could be made. And I'm going to show you how you make modules out of that, because although there's a lot of work that's been done on identifying the right materials for different separations, and ways you make those materials into films, into sheets, I think one of the key aspects, a key enabler, is how you make the modules out of that. And I'm going to talk about some patents, which I think should be required reading for anybody that's interested in membranes. If you're interested in membrane technology, read these patents right here. Because this work, they're directed toward gas separation. Although it's directed toward gas separation, it was motivated, a lot of these design steps here and processing steps were motivated by work they did for desalination initially under the Office of Saline Water. So highly recommend you read these patents. Once you take this fiber up on a spool, what they describe is how you make it into modules, useful devices. You take these spools, you put them in a bunch, an array over here, you pull the fiber off those spools, and you wrap them around this device right here. You can see there's multiple filaments. There's 4 filaments that are being wrapped continuously around there. What Maxwell and his coworkers at DuPont taught us is that you take one of these spools or these filaments, continuous filaments that's been wrapped, and you stretch it out, and then you pull a sock over it. This little thing right here is an elastic sock. The reason you put that sock over there is hold the fibers in roughly a uniform configuration relative to each other. This element, this sock wrapped tow, then a bunch of these get hung together from a plate like this. This now forms our macroscopic module. To hold these individually wrapped fiber tows together, another sock gets wrapped around it. Once again, the purpose of that is to hold them such that they're uniformly spaced relative to each other. You don't end up with big gaps between them. Once you form this sock-wrapped module, a case gets put over the end of it, right here. Here's the sock-wrapped portion of it. Here's the case that goes over the top. What they suggest you do then is you take this module, you put it into this device right here. What this device does is it rotates. As it's rotating, an epoxy is fed from these pumps and these reservoirs up here into this cap here, which is a mold. The epoxy will flow into that mold and harden. And as it does that, as this rotates, the centrifugal forces will keep the epoxy from wicking up into the fiber bundle. You form a nice edge to this tube sheet that's being formed. Once you epoxy encapsulate the end of this bundle, we can cut it, which will allow us to open up the fiber lumens and get access to the fiber lumens. And then prevent the epoxy that we put into here from wicking up into the fiber bundle by having it rotate like this. Once you take that module, you put it into a case, you end up with something that looks like this. This is a typical hollow fiber module. And it looks like a hollow fiber heat exchanger. It's a mass transfer equivalent of that. If you look at this, what you have is a port on the outside to allow you to introduce a fluid such that when it encounters this tube sheet, which we just formed by rotating it, the centrifugal potting process, once it encounters it, it's forced to flow through the lumens of the fibers where it comes out an opposing tube sheet and then through that port right there. Anything that permeates across the fiber can be removed, or it permeates across the fiber into the space outside the fiber into the shell can be removed from ports that are attached on the outside of the case. If you have two ports, what you can do is you can introduce a sweep fluid through this shell space as well. The other primary module design is makes use of flat sheets, and the two early patents associated with that are due to Westmoreland and Bray. Westmoreland's is probably the easiest one to understand because what he proposed is just taking two membranes, this number 20 and this number 18, and between them putting a mesh. That's this number 24. So you have these two membranes, and between them is a mesh. You glue those two membranes together to form a sheet or a little leaf. In operation, what you do is you pass seawater across the top of this. As it passes from the bottom of the image here to the top, as it passes across it under pressure, fresh water will permeate across the membrane into the space between the two formed by that spacer. The glue lines that exist all the way around the sheet force the liquid that permeates, the water that permeates, to flow toward this collection tube here. The sandwich is glued to these ports right here. It's in communication with these holes on the collection tube and allow you to withdraw the fresh water. A key design element is allowing you to put multiple sheets into one circular package, one module. And that's what's shown here in the patent by Bray. I'm not going to go into the details of how you do this. The reason you want to put multiple leaves in there is that there's a pressure drop associated with flow through this leaf. And if you make it too long, the pressure drop kills you. So you have to put in multiple leaves with a spiral wound design. You put this whole thing into a case, the spiral wound module. It has ports on it that allow you to introduce a feed, pull out a reject, which is what doesn't permeate as it flows through the module. What permeates across the membrane and into the space formed in that leaf by the collection, the permeate collection spacer, comes out through this tube right here. Okay, that's membranes past. Now I want to talk about membranes present. What this slide shows is the current membrane market. It's roughly $3 billion per year, according to a study done by Fredonia Group. And it's broken into these categories right here. Microfiltration makes up 45% roughly. Then reverse osmosis, ultrafiltration, and then other apps are down here at 13%. This includes primarily gas separation, and primarily in gas separation, nitrogen production, followed by hydrogen purification and CO2 separations. So it's a huge market, and it's expected to grow at almost double-digit rates through 2012. Now, what's not shown in here is dialysis membranes. Dialysis membranes really are the largest market, but these are just membranes in industrial markets, not medical markets. This is the lobe suryagen membrane over here, showing the porous support underneath, and on top the perm selective layer. Currently, a number of membranes do not consist of this asymmetric structure, but consist of a composite membrane structure in which you form a porous support separately, or it can be formed at the same time perhaps, on top of which you put an adhesive layer, or gutter layer, on top of which you actually put the perm selective layer. This is not this asymmetric structure, but a composite structure consisting of these three different elements. This separate porous support can be made of a different material than the actual perm selective layer on top there. This adhesive and gutter layer here in between the support and the perm selective layer, as well as a top layer here, protective layer, help seal out defects as well as provide mechanical strength and protection to the sandwich. So these composite membranes are becoming more common relative to these asymmetric membranes. Current manufacture does not look like it did back then. Film hollow fibers still are spun using a similar process, but instead of them being wound or formed into a module like I showed you before, they can be woven, and this is becoming increasingly frequent, can be woven into a fabric as through this loom right here. This fabric then gets wrapped around a spool to form a module. Instead of centrifugally potting these modules, what you can simply do is just dunk them into a bucket, fill the bucket with epoxy, and you can form a tube sheet that way. This is a much simpler process and a much more common one nowadays. In terms of spiral wound manufacture, you can, instead of having just a single sheet like this, a single leaf in which you're forced the permeate to flow in a cross flow direction relative to the feed, this black arrow, you can actually put glue lines inside the leaf to give a countercurrent flow inside the leaf, as well as allow the introduction of a sweep into that leaf. And also there's lots of effort going into how you produce modules that have many, many, many leaves in them. Okay, so we talked about drivers, enablers for membrane technology. Talked about the past very quickly, very briefly. We talked about where I think the current state of the art is. Now I'm going to talk about the future. This is going to be primarily on markets. There's a whole bunch of areas that people are arguing you'll see membrane technology. You can read through that list here, from solvent nanofiltration, virus filtration, to hydrogen purification, very special metal membranes that might be used in that particular case. I'm going to highlight a couple of these areas that I find interesting. I hope that you find interesting as well, that aren't listed here. First two are on this slide. What is shown here is projected market growth by BCC Research in the membrane bioreactor market. Membrane bioreactors commonly have a configuration that looks like this here. This is a Z-weave membrane cassette. They consist of our hollow fiber ultrafiltration membranes that can be used in the clarification step in a wastewater treatment plant. What they're able to do is greatly enhance the ability to treat the mixed solids, the mixed suspended liquor solids removal that's produced by a biological treatment process. What you can do is pull a clarified water through the fibers here, and you can produce a higher quality permeate and increase the capacity of the treatment process dramatically by using this membrane technology right here. And that's why you're seeing a growth from where we are right now in 2008 of about $300 billion to $500 by, that should be 2013 right there. And about a 10% compounded annual growth rate. Another area that I think we'll see increasing interest and demand in is in carbon capture. Once again, BCC Research predicts that if we look at both pre-combustion and post-combustion carbon capture technologies, they're going to grow from levels that are on the order of 50 billion a year now to levels that are over 100 billion by 2012. Where can membrane technology have an impact here? And there's two areas where they can, I think, have a dramatic impact. One being in pre-combustion, one being post-combustion. Let's first off talk about the pre-combustion area. What you can do is make use of a membrane process, which John, I think, did mention a little bit, not with membranes, but with cryogenic distillation. You can take air, produce oxygen, and use that to burn whatever it is you're burning. And the gas that you produce, the flue gas that you produce, is predominantly CO2 and readily sequestered. Well, instead of using a cryogenic technology, we can use the membrane technology. One of the very interesting materials for doing this is these oxygen-conducting perovskite membranes. What they do is they're 100% selective to oxygen. And so if you have a material like this, it will produce a pure oxygen stream which you can feed then to a burner like that. And there's two groups that are looking at commercializing these things. One headed by Air Products, another one including John's company Praxair, BP, and Amoco. These companies are putting significant investments in this technology. And I think even membrane technology has an opportunity here as well. Another area where our polymeric membrane technology has potential here as well. Another area where you could potentially use membranes in post-combustion, where you can use a polymeric material to selectively remove CO2 from the flue gas. A very innovative process proposed by MTR is to use the air that you feed to this as a sweep on a stripping stage, as a second sweeping stage. This could allow you to dramatically increase the recovery of the CO2 while simultaneously increasing the content of that product stream that you produce there. Another area is in bioethanol. If you take the fermented mash, currently it goes through a beer column which takes it overhead and then to a rectifier and a stripper. What you can do is replace the stripper and the rectifier and the subsequent molecular sieves with 2 membrane units. This is remarkably similar to, I think, where we were in desalination about 30, 40 years ago. Here we are, we can replace 2 distillation columns with membrane technology. I think that we can see comparable energy savings as well as cost reductions in the bioethanol market. One area that's a little further out is how can we produce energy from where fresh water mixes with ocean water. This diagram here is supposed to show where river water is coming and flowing into the ocean over here. We can just run this through a reverse electrodialysis unit where we have alternating cation and anion exchange membranes. As the fresh water flows through and we exchange the ions from the seawater with the fresh water, as they move, they carry a current with them. We're able to produce electricity from that. So you can imagine putting these reverse electrodialysis plants wherever we have rivers, large streams going into the ocean and producing electricity for free, except for the capital cost of the plant. And I have 2 other slides I just want to mention is where are the future materials? I think the future materials are going to come from composite materials, ones in which we blend the properties of polymeric materials with inorganic materials or solid materials. And these mixed matrix materials have the ability to allow us to increase the permeability of a material while down here, the permeability, while simultaneously increasing the selectivity. And what's shown on here are the results for mixing a zeolite 4A in with a polymer, this polyether imide, Ultem 1000. And you can take the polymer, and by mixing in the zeolite, you can change its permeability, increase its permeability, as well as increase its selectivity and move in this direction from the pure polymer up to regions here where we have a significantly higher selectivity as well as a higher permeability. By properly controlling how you put this zeolite into it and perhaps adjusting the interface region between the zeolite and the polymer to improve the adhesion, that interface region, so you don't have either gas bypassing around that interface or gas being precluded from entering into the zeolite. I won't go into the details here. And finally, I just want to talk about carbon nanotubes. Carbon nanotube membranes, where you disperse carbon nanotubes, could be multi-walled or single-walled nanotubes into a polymeric matrix, have very exciting properties. You can increase gas diffusion coefficient by a factor of 10 due to specular reflection. You can potentially increase liquid flow rates through membranes by a factor of 10,000. These are huge increases due to the nanostructure of the pores that exist here and the fact that they are nice and straight. I think that this is an area that we're going to see a significant amount of research activity in over the next few years, next decade. Eventually, you can even put gatekeepers on the mouth of the pore there. With that, I'll conclude. Just want us to emphasize that this industry that we're talking about, this $3 billion industry, has just emerged over the past 50 years or less. That government support was critical to making this happen. The Office of Saline Water was, I think, such an important factor that we need to encourage, we need to tell the government, this is what happened once before. You need to consider doing this again because look at what you can do. Energy concerns are going to drive a significant growth of the membrane market. And finally, I think that we're going to see its impact in many industrial sectors because of its ability to reduce energy consumption. I'd like to thank Bill Poros for providing some of the graphics you saw. Keith Murphy was part of a brainstorming group on how membranes can reduce energy consumption, and Neil Chung helped me give me some time to work on this while I visited him. With that, thank you for your attention.